All right, here we are once again back in Pony Island. Our next step in terms of completing objectives in the game is to tackle unbearable revenge and along the way get the achievement for the right to arm bears. But we've got a little more work to do before we're really ready to do that. I wanted to do a deeper dive for everybody on Cheat Engine, Ghidra, and that sort of thing. And also, there are, of course, going to be certain things that we can't influence with our own internal cheat, our own trainer, because this is an MMO. So we essentially have an application in a client-server configuration. Certain things will be done client-side, certain things will be done server-side, and we can basically own the client processes, but we have no influence over the server processes except for what the client sends it. And so we need to write ourselves a proxy to essentially intercept packets between the client and the server, inject our own packets to the client and the server, or alter packets to the client and the server. Now that's going to be a separate video, obviously, because writing a proxy is a different thing. So we have two videos we have to do before we can actually get to the right to arm bears. And one of them is going to be on Ghidra and Cheat Engine and other local cheats, and the other one will be on writing the proxy. And so we will start with what we've already started with, which is Cheat Engine and Ghidra. We're going to do a little bit of a deeper dive on that in this video. So before we do that, let me show you the current state of my trainer, I guess. So if I go here to Cheat Engine, I am going to click this button and I'm going to attach it to the game process. Done. And let me load the table that I saved here with all the values that I've been working with. I'm going to get rid of these. These are just, well, we'll get into this here in a little bit, but don't need those for now. So over the last week or so, playing around in the game, I have been poking around at all of the addresses associated with the processes and have been figuring some things out, and I think it's about time that I stopped and really explained what's going on here. So as I mentioned in my previous videos, this up here and this here, during that first video where I introduced Cheat Engine, I was looking for the mana values, and so I ran a couple of searches. When I found those, I basically wanted to find where those addresses were homed, so follow the pointer path to the origin. And notice that it led me to 3F2FOE34. Now this is a relative address, so this is different than the first time I found it. It's relative to essentially where it is originally called in code. But that allowed me to find first, the home for GameLogic DLL. So right now, 7964000 is the top of GameLogic DLL in memory. And then I was looking for the speed multiplier, the float of 3.0. Some searching led me to this address, and this address I found in the code in Ghidra. And I found the offset for that variable. And so GameLogic DLL plus the offset for that variable leads me to that variable, regardless of where GameLogic DLL happens to be in memory. It's always going to be this address. GameLogic, looking around then, led me to a discovery of a game world label, which contains a player object, right? So here's game world. The value here, irrelevant. I just added it to my list so that I would easily be able to see what the top of game world is. And then I found that the player object is instantiated in game world under that label 2C. Offset 2C from the top of game world. So here's the top of the player object. Also, again, ignore the value there. It's irrelevant. Notice that it's changing quite a bit. That's because the game, essentially, there's a tick going on. And so every tick, this value just happens to be changing. We'll get into that, though. So once I found the top of the player object, I wanted to see all of the attributes that were associated with it. And in the process, I found a value of 100, and then shooting a couple of fireballs in the game, I noticed that the value changed. And I looked at the address, and I noticed that it's the same as what I found before. So these pointer paths would have shown me where the player object is before. I just didn't connect the dots. But after this, I definitely did. And so I knew I was looking in the right place because, generally speaking, with an object, it's going to have attributes associated with that object very close to each other in memory. So I was able to find the jump height value, which means I was able to change it, which I did in the jump height video that I posted yesterday, but I recorded last week. Then I was looking around for other values. I found in the code that there is a can be damaged function that's associated with the player, and I think I found it, but it doesn't really seem to work, so I'm not entirely sure that that's can be damaged. But I found another value of 200, a float 200.0, and then another value of 420.0, and after some experimentation I realized that that's our walk speed and that's our jump speed. So what I found before was our speed multiplier, right? So when we are running, we are 3 times faster than our walk speed. I was looking around originally for what our walk speed was so that I could change that, but instead of having a raw value, it had a M remote look position along the X vector. And I didn't bother tracing back because I was looking for a raw value. I wanted to basically do a live bin patch rather than actually writing. I wanted to demonstrate 2 ways, essentially, of doing a cheat. But now that I found walk speed, I could change my speed hack so that instead of changing this raw value, it finds the pointer path for walk speed and just simply increases that. It does the same exact thing. In my jump video, when I found the jump height variable, changing that did change my jump height, but I also floated around really slow with that. So after a little bit digging around in that 420.0 value, after messing around with that, I found that to be associated with jump speed. So the speed at which you accelerate along the z vector when you jump. And so now I've altered my jump hack so that it changes both the jump height and jump speed. So not only do I jump high, but I also jump at a more reasonable pace. It's not a slow float any longer. I also found in that player object the player name and team name. So note here is a string 12, and that is indeed my character's name. So I found all of this through the process of reverse engineering, but obviously, saying it like that is not really that helpful to you, so I'm actually going to show you some of those things here today. But first, let me demonstrate where my trainer is at these days, my DLL. So I'm going to go to Memory View. All right, that shows us just raw memory offsets here. I'm going to Tools, Inject DLL. So there's my Pwn Hook DLL. This should be the newest version from 2 days ago now. Inject that. Here's the console that I created, DLL injected. There we go. So there's the current jump height, that's correct. The current speed, that's correct. And here's, I was trying the piece hack because I saw the can be damaged. I was experimenting around with that. I was going to throw that into the trainer, but haven't quite cracked that one just yet, so don't worry about that. But now if I go in the game, regular speed hack on, very fast, just as before. Jump hack on, and now with both of those variables being changed, I jump high and fast. Now I could adjust either of those values so that I jump even faster or jump even higher, but I felt like this is just fine. It's faster than the regular slow jumping speed, but not so fast that it's like I can't, figure out where I'm going, or it's just easier for me and my weak brain to understand, where I'm going and how to get there. The goal here is when we get to Unbearable Revenge, I will use the jump hack to jump into a tree, but you'll see when we get there how we do that. Yeah, there we go. This will do just fine. As long as I can make it up into the tree, it's good enough. At any rate, so we're doing good. All right, we got a couple of decent hacks going on. I'm going to leave the town here a little bit and go somewhere where I'm less likely to run into students, because I don't want to disrupt anyone and the work that they're doing. So, and okay, I'm on top of the mountain. All right, so let's look into this a little bit. So where should we start? That's the question. Well, first, let me open up our DLL here with Ghidra, so I get back to that. All right, so here's our Ghidra. Cheat Engine here. Let me close our memory viewer. Since the DLL is injected, we'll do this one thing at a time. All right, so in one of our first videos, we were looking for our mana value, right? So we have in the lower right-hand corner there next to the inventory bar, blue bar for mana. Whenever we cast a spell, of course, our mana goes down. And our mana is going to go down by a certain amount for every spell we cast. If we cast just one, it goes down to 96. So we can see that each fireball is 4 mana. We know that it's one of the variables that we want to influence, right? And so in our first video on Cheat Engine, I walked through very briefly the process of how do we find values in memory, okay? I'm going to go ahead and do that again, just this one time here for you. I don't want to retrod ground, but I went through it pretty fast before, so we'll go through this time a little bit slower. So once Cheat Engine is attached to the process, we basically have an external program that is able to access the memory space for another resident process. In this case, whatever we attach it to, our game client. Our game client was launched, right? And it's got code in it. It's a compiled binary, and it's got basically what it needs in order to do the client process, right? But it doesn't contain any of the game information. All of that is in another area of code, which is a DLL, gamelogic.dll. But when we launch the client, it looks for the DLL, finds it, loads it, so it's all kind of in the same run space. The DLL is not a separate resident process. It's a dynamic link library. It resides within the memory space of the process. And the original process contains a certain amount of memory, but it will extend and request more for that DLL process, right? So, what was I getting at? Oh, right. So, Cheat Engine or our debugger in this case are able to view search at least the values in that memory. It has access to that memory space. Not all memory is going to be readable. Not all memory is going to be writable. Well, it's all going to be readable by the process, but not all of it's going to be writable, and not all of it's going to be executable. Depends on different areas of memory and the compiler and various different rules and so on. So the question is how do we find that value in the game? Well, as I showed before, number values, you can search for them in memory, right? They're going to reside in memory, not necessarily as the raw value 100, of course, because it's going to be bytes, but we can ask Cheat Engine to translate our input into bytes and search for bytes in memory, right? So if we say, well, we know that we have 100 mana, right? This is as we saw before. We have 100 mana. The question is how is that going to be represented in memory? Is that game considering this an int? Is it a float? Is it a string? Is it a double? And as we talked about before, this is a 32-bit application. 32-bit applications have memory addresses that, of course, can hold 32 bits. And an integer on a 32-bit system will be 4 bytes. So we know that if it is held as an integer, that it's a 4-byte value. And we did look in Ghidra, and we saw that it appeared that the code was declaring the value for mana as an int. So we know that it's 4 bytes. So we search for a 4-byte value with the exact amount of 100, because we know it's 100 here in the game. Now, do we know that for sure? No. I mean, looking through Ghidra and finding the code, yeah, I mean, we can figure that out. But even if we didn't do that, we could take a pretty good guess. And if we didn't find it, a value of 100, well, that's fine, because it's still got to be somewhere, right? So let's do our first scan here for the value of 100. All right, and we have 9,743 different memory addresses that have the value of 100. If we scroll through the list quick, we can see that, well, here's one right now. It seems to be changing. The value going from 100 to 8 and back and forth like that. I bet if we sit here long enough, we can probably find a correlate here with something in the game. It looks like it might be tied to the tick. Yeah, it almost certainly is. I'm noticing that it's changing not necessarily on every tick, but regularly and in time with the ticks. I don't know what that is. I have no way of knowing. We could explore if we wanted to, but it's probably not worth our time. The rest of these here, do we have any more changers on our hands? There's one. This one's going from 100 to... Let's see it come back. Well, that's far more irregular because it's not coming back. And there's another one. So we have some of them that are changing. But our mana isn't changing. It's still at 100 and it has been. So we're going to go compared to the first scan. It will be an unchanged value. And this will hopefully weed out some of those memory addresses that are changing because we know the value we're looking for hasn't changed. So we'll go next scan this time. And it got rid of about 20 or 30 of them or so. Now we're at 9,716. All right. Now, the best way to try and find the values we're looking for is by changing those values and then running another scan based on that change. We can influence the amount of mana that we have by using some of it. So I'm going to set this up, and we're going to say this will be a decreased value. Now, if I can control the amount that I'm losing, you can enter a specific amount. Like I could say decreased value by whatever, and we know that each fireball uses 4. The problem is that we start gaining mana the moment that we lose it. Basically, every tick we get 1 mana. So by the time I switch back to Cheat Engine in order to run the scan, it'll be too difficult to tell exactly what the amount it will have decreased by is. Had to resituate myself here. Had a little bit of a crash. Not a problem. We're back. Okay, so I'm going to just start a new scan here now. Value of 100 for scan, 9,150. Compared to the first scan would be unchanged. Next scan, 9,129. So about where we were before. Okay, so now I can change that value by using up some mana. And that should be enough. I can hop back and it will be decreased compared to the first scan. All right, so we went from over 9,000 to 85, right? We can also see that some of these are definitely associated with mana. Like right here, that one is ticking in time with our mana. We can see down here below. There's going to be others because we know from the first time we did this that there were 3 that were visible. All right, but now we're back to 100. So now we're going to compare to the first scan, and we're going to go with unchanged compared to the first scan. Now we're down to 28, and we'll go ahead and decrease it one more time, and we'll do a decreased value compared to the last scan, although the values are identical, so it really doesn't matter. Good enough. And next scan. All right. So we have this one here we already have. This one here. And this one here. The first time we did this, we indeed also found 3 values. So we found 3 here again. Why do we have 3? Well, there's a couple of reasons why you might see 3 variables that represent the same value. Number one, it's possible that a value is represented for different reasons in different areas in memory. So, for example, we can see the number 100 here in the GUI. Does that necessarily mean that mana equals 100? Well, not necessarily. Maybe that's a display value. Maybe mana is actually a float, and the display value takes the value of mana and then truncates everything or rounds up or down based upon the decimal value, and then just represents it as a whole number. So yes, you might have a value that's identical because it's for a different purpose. Maybe it's used in some other calculation for some other reason. None of these are really best practices or even necessarily that sensical, but I mean, programmers make odd choices all the time. It could be, essentially. The most common reason, however, is because a variable must span more than the available space. So we have a 4-byte value here. But how much space can a single memory address hold? Well, a single memory address can only hold so much, a finite amount. And if the value of the variable is greater than what a single address can hold, obviously it will need multiple in order to hold the entirety of it. And so you'll have the first part of the value in the first address, and then a pointer that leads to the next address that has the next part of it, and then a pointer to the next part and the next part until eventually we reach the end. In this case, in order to hold the mana variable, we need 3 addresses. Hey, excuse me while I interrupt myself here, because I find myself wanting to ensure that the explanation here of what we're doing is a little bit more clear. So, to begin with, let's talk about pointers and what we're actually looking at here. So, let's say that we have some code and we want to declare a variable, an integer in this case. We'll call that v. And so we go int v equals, and then let's say 100, which is exactly what we have here for our mana. Now, what that means is that when this code runs, there will be an area of memory. We'll put it in a little box here. And that will hold a value, and the value will be whatever we assign to it, in this case, 100. Right? Now, of course, it's not going to actually hold the integer 100. It will instead hold a representation of that in binary or in hexadecimal. We can use byte pairs, and hex 64 equals the integer 100 or decimal 100. Okay? And of course, I'm not going to do the binary translation here, but this is just a representation of that. Now, this location, this box here, we need to, there's an address for that, right? There's addresses for every discrete block of memory in pretty much any computer. So we'll say that this is memory address 2A49. The actual address doesn't matter much because, of course, that can change. So we'll go with 2A49. Now, when we're reading code, if we see, or writing code for that matter, if we see the following, let's say that now n equals, and I can't really do the ampersand. Let me give it a shot here with the mouse. Okay, that'll work. If we have int n equals and v, what the and there represents is that we are referring to the address for v, where v resides, and not the actual value of v, which means that now n, we'll have another little box here, and n now equals to A49. Okay? Which means now if I were to do math, by the way, if I were to say n plus v, what I would get is hex 64 plus hex 2A49 equals whatever. We also in code might see, let's do another variable here, where, how about it equals, how about z equals asterisk v. We have another little box here in memory. And now, oops, z, not x, will equal, the asterisk there shows that we are looking for the value. So we go to the pointer and we find the actual value at that address, not the actual reference itself, which means we're back to 100 again. All right. This also means that if we were to, let's say, change, we can declare this either way. So we can say v equals 20, then we're actually changing the value of v to 20, but if we refer to the pointer instead, then it would change the pointer address to 20, and that's not going to help us because who knows what's sitting there at that address. Right, so that's roughly what we're talking about here, because when we declare a variable, it goes to an address, and we can put that address into other variables, and this is called a pointer, right? It's pointing to a memory address which contains a value. Now, as I mentioned a little while ago, not all variables are going to span, a single discrete amount of memory space. You might need multiple addresses. Actually, hold on a sec. Let me pull up an example here. All right, so I have a little program here in C to help visualize this a bit. let's start by declaring our variable as 100. Let me fortify my font size here. Save that. All right. So all this program does is takes that variable and then prints out the byte values here. So it's an int, which means it's 4 bytes, and because it's a computer system, it starts counting at 0 rather than at 1. So 0, 1, 2, 3, that's 4 bytes. A byte, 8 bits, is a byte. So each of these bytes is 8 bits. And we can represent a variety of numbers with bits. Of course, we can use hexadecimal to create byte pairs. So 0, 0, 0, 0, of course, would equal 1, 2, 3, 4. 1, 2, 3, 4. That's the binary for that. Whereas 0, 1 in hexadecimal would be 0, 0, 0, 0, 0, 0, 0, 1, and so on until we get all the way to the top of the hexadecimal chart for a single byte, and then we have 1, 1, 1, 1, 1, 1, 1, 1, right? Now with that, how many numbers can we represent here? Well, if we go through the line and we say, okay, 0 is one number, right? So then all zeros and then 1, 1, that's another number. We can represent 16 on one side of a byte pair and 16 on another side of the byte pair, right? And if we do the math on that, uh, 16 times 16 is 256. So we can represent 256 numbers, decimal numbers, with a single byte, with 8 bits. So if we have a variable that is 100, we can easily represent that within 256, right? Which is why we have a byte 0, which equals 100. That's just, if we were to convert that to binary, let me see. I'm not entirely sure off the top of my head. So we know that that first byte right now looks like 1, 2, 3, 4, 5, 6, 7. There we go. That's what that first byte looks like. The second byte is 0, so we know that that's 4, 5, 6, 7, 8. The second one is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That's what those 4 bytes look like right now. All right. So what happens if we have a larger number? Let's say we change this to, how about 1,000? Okay, so now if we run this, we can see that the first byte is 232. The second byte, or the byte in the 1 position here in this case, is 3. So how does that equal? How does that equal 1,000? Well, the second byte records how many of the first byte have been completed. So essentially, how many 256 counts do you have? And then the bytes below that are single digits again. The third digit, so in this case byte 2, records how many byte 1s you've had. The third one records how many byte 2s you've had. So essentially, we have 16 times 16 for the first byte, which gives us 256 possible numbers. And then we have times 256 for the second byte. That gives us the magic number in computer, 65,536. And then how many 256s have we had on top of that? And then for the last byte, how many 256s have we had on top of that? And we arrive at 4.295 or 4.3 billion as our final number. So we end up with 232 plus 3 equaling 1,000, because if we take 256 times 3 plus 232, we get 1,000. If we have exactly 256, and 256 is the limit, but remember it starts at 0. So if we put 256 in there and we run it, we end up with just 1 in the second byte position, or byte 1 in this case. Okay. So pretty much what we have is we have 4 byte values, or we have 4 bytes in memory. Those 4 bytes equate to, so what we actually have in this case is something of, I guess, a little bit of an idiosyncrasy or an inefficiency, because what we have here is an int, and ints are always 4 bytes, no matter how big they are. So an int will be 4 bytes, whether it's just the number 1 or if it's the number 4 billion. In this case, we're only using one, not even a full byte for the number 100. And yet our pointer paths are also always going to be 4 bytes. So we have pointers that point to a value, or in this case, 4 bytes worth of values, to point to a single byte of value. So we're actually wasting some space with the variable itself, but then even more by referencing it multiple times at different paths, different addresses. Because this is a 32-bit system, so 2A49 here, that address, you have to basically think of each memory address like our the variables we just saw, the byte values that we just saw, are also represented in hexadecimal. So we can have a memory address here. If we just have a memory address, let's say FF, well, that's a 1 byte. This is a byte pair, so 4 bits, that's a byte pair. So this is 1 byte, and let's go ahead and we'll go down the line here. So that's 2 bytes. Three bytes, and 4 bytes. So this is a 32-bit memory address right here. Hence why we, in Cheat Engine, see 7AA20000 as the top of the address, for example, for GameLogic DLL. It's a 32-bit address. So it's just something of a little idiosyncrasy, because we have variables. Right, so we can actually have variables that point to pointers. Right, so the value of n in this case is going to be this address, the address itself. And then what is in this address? The value that we first assign. Well, actually, this would go down here, wouldn't it? The value we first assign. So it's a little bit of an inefficiency, but I mean, overall, things run more smoothly when there's consistency, and we're not constantly trying to make things as efficient and as possible. Okay, just wanted to make sure that that's clear what a pointer is and what we're looking at here in terms of memory addresses and variables. Okay, think of it like, I mean, the common analogy is to think of pointer paths as being to think of pointer paths as addresses. So if we have a street here, and we have houses on the street. Oh goodness. Okay, there's no building codes here in this neighborhood, so. All right, so we have a street, and this is 23 Elm. This is 24. 25 and 26. All right, so you know, who lives in house number 1? House number 1 contains Professor Johnson's family. This is my actual literal address, by the way, so feel free to come visit me at 23 Elm Street. So that's what it contains. Right? It contains the Johnson family. But what is the pointer to the Johnson family? Well, the pointer is 23 Elm. Oops. Okay, good enough. Right. That's the popular way of thinking of it. When it comes to the confusion over the pointer pointing to a specific amount of data, you can think of it like pages in a book, right? So if the page number, if I say the page number is page 32. Right? That doesn't mean that the page contains 32 words. It doesn't mean that the page literally says 32. Of course, there will be a page number printed on it, but that's what pointer paths are. They point to the next pointer. But it doesn't mean that it's just a page that says 32, because of course the page is going to contain all kinds of words all over the place. There's a book. 32. And that's our pointer. And this is the data. All right. Now we could consider the whole book as being a variable, right? And of course, that's going to extend far beyond a single page. So every page has to go to the next, has to go to the next, has to go to the next, and that would be pointer paths, right? So if you start at the last page of a book, if you want to start the book, you have to go to the first page, right? And then the first page leads to the second, to the third, until you get to the end, and that's a pointer path. Okay, I hope that makes more sense. Let me get back to what I was saying before. Together, they all equal 100, right? But as we saw before, if I change the value of the first one, it just gets reset to 100. If we change the value of the second one, it just gets reset to 100. If we change the value of the third one, well, that does change the value in both of those other addresses, but also the value here on screen. The issue is that if I fire a fireball, it doesn't count up from 50. It just goes to 96 and then counts back up. So we have a conundrum here. Either what we've discovered here is only the display variable, as in this doesn't actually represent the amount of mana we have. It represents instead the amount that's being represented in the GUI. Or we have another issue where with the online version, the amount of mana that I have is not actually kept by the client, it's kept by the server, and that is what determines how much mana I have. Essentially, the server updates the client. That 100 value that we have here is coming from the game world information or the player object information on the server side. Now, luckily, there is a way that we can tell. There is an offline version of this game. So let's log out, and let's go offline play. And I'm going to need to create a new character here. I'm just going to use the cop again. Notice you don't have to choose a player name or a team name for the offline version, but my cheats still work. I still have super speed, even in the offline version. Let's also check the state of our values here. So game world, player, these don't seem to be the same values. And yet, speed multiplier is the same. Why is that? Because that value is hard-coded in code at that location. So it's always there regardless of whether we're online or offline. I'm going to actually turn it off for a second here, though, because it's a little bit too fast for in such a cramped quarters here in the cave. I'm going to grab the fireball spell so that we have a spell to cast here. Excuse me. Okay, we learn the spell. Get the achievement for the offline version. Okay, and then bounce off the rocks and get up there. I'm going to move somewhere where I get a little bit more space to do this. Not because I need the space, but just because I will be more comfortable with the space. So, okay. All right, so this is the offline version. If you skipped ahead and you're not sure, what I'm doing here, or if you're trying this later and it's not working, it's because I switched to the offline version of the game. And the reason I did is because I want to see if I influence those values in the offline version and I have infinite mana, then I know that the values are being updated or kept on the server. If I don't, then I know that they're just display update values. But note, we do still have 2 of our addresses that we found here are represented by the correct value, but one of them has reverted to 0. That's actually interesting. It required 3 addresses before, but 2 now then we're almost certain that for some reason that value is being kept elsewhere. I almost wonder if this is the mana version that is being reported or gets reported up or updated by the server, and these are the local variables. Well, let's find out. We're going to check this. Actually, before we check the box, let's change this value back to 50. Okay, that didn't change our mana. What about this one? No, it's not. All right, Control Z that. I guess let's start a new search. Let's see if we can find the mana variables there, because these don't seem to be it. At least it didn't update when I changed the value. So we'll start from the beginning. Looking for 100 here. 10,247. Okay, it will be unchanged from the first scan. We'll give it a couple of seconds. Doesn't look like they're really changing. Yeah, we only lost a couple of them there. Okay, so let's get ready to search for a decreased value compared to the first scan, and we'll use up some mana. Good enough. And next scan. Okay, we're down to 90. This one is clearly related. I thought I saw one here that seemed to be in sync, but apparently not. Let's try this value here. Oh, see, that is the value we saw before. So this is still related to mana somehow. It's just not the one we're looking for. I'm going to get rid of this one because it's a duplicate of the first one we found. And let's do it again. I'm going to use up even more mana because I'm going to do another decrease scan. I'm going to do compared to the last scan. So I want to make sure that I use up even more mana than I did before. So decrease compared to the last scan. There we go. We've got 3 values again for mana. And this is a duplicate of the one we saw before. And this... Oh, the other two are actually just... They're very close. They're adjacent to the old places in memory. Like, for example, this one's 37F72B44, and this one is 376FF984. And the other one was 4E5A2EFC, and this one was 4E5A369C. So same, just different offsets. Okay. I'm going to let this tick up, and let's see. In our first version, it was the higher address here, the 4E address. That was the actual value. So let's try that one. Okay, so that did change our mana. But also, look, in the online version, when we changed that number, it didn't start ticking up. In the offline version, it did. Almost as if it didn't just change the value that was being displayed, but it actually updated the amount of mana that we had to the new value. So if I change that value again, let's change it to 0. It starts ticking up right away. So it's different behavior that's very interesting, and I think that answers our question. If we go to the online version and we update that value and it doesn't start ticking up, then as far as the game is concerned, we didn't use that mana. It's not activating the portion of the code that begins the regeneration process for mana, but in the offline version it does. And so that difference in behavior tells me that mana is probably handled server-side somehow in this game. Let's update that value back to 100 to give ourselves full mana instantaneously. And now let's hit this checkbox for active. And what that will do is basically it will hold that value static. So we'll be at 100 no matter what here. We might see a little bit of a blip as the value is updated, but then are reverted back. But it should remain pretty much at 100. Indeed. And every single time I hit it, I can see it flip very briefly to 96, but it never goes lower than that. So effectively, that does give us infinite mana in the offline version only. We can't do this same trick in the online version because only some of this is handled client-side, and none of the important bits are handled client-side when it comes to mana. But that begs the question. These values changed, right? The only one that didn't change is this one here, the ODDAF338. It's the only things that didn't change. The only one that didn't change. The other two did. So does this mean that every time we start the game, we're going to have to do the same process of searching in order to find the location of the mana variable just so that we can hit the active button and toggle it on? No, it's not. What we need to do is basically we need to not just find the address, we need to find the pointer path that represents where that value is likely to be stored. And from there, if we can record the pointer path, then it will be a relative offset that should be consistent. Because, I mean, notice that the addresses are different, except for the very end, right? The last few bytes. Because while the address is randomized, the offset has to be consistent, right? So we can actually find this value. If we right-click here, we can go to pointer scan for this address, all right? And that will launch us up here. And you might have to generate a pointer map for this first if you haven't done it before, but not a problem. Scan for address. Scan for address with value, so we could basically run our search along the same as the scan, or generate a pointer map. So if you haven't generated a pointer map, you might have to do that. And then you might have to use... let me try running this without using the saved pointer map and see what happens here. Max different offsets per node. Leaving it at 3 is good. If you find a pointer path with more than 3 nodes, then it's not going to be much use to you. Because the pointer paths may change a bit from run to run for the game. So you want the absolute shortest pointer path that you can possibly get. Let me show you what I mean here after the scan runs. We're going to leave everything else default here. We're going to save this. Sure, I'll save it as the pwn3 pointer from the last time I ran the scan. No problem with that. So it's going to generate a pointer map on the fly because I'm overwriting my former pointer map, and I didn't ask it to compare because I wanted to do this as part of the demonstration. But generally speaking, once you have a pointer map here, you're fine. All right, so here's our pointer scan based on that address. So the 43A blah, 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 blah. Here's the value, right? And over here we have offsets. Let me expand this out. So here we have our base address. This is the client exe plus an offset. And then we have offset 0, 1, 2, 3, 4. So this is a 6 offset pointer path. That's not really going to do us that much good, right? Because that's just extremely long, and that's likely to not be the case. The next time this runs, it's likely to be different. So let's sort by the offset here, offset 2. Because we want the absolute shortest. Holy moly, we have the shortest we can possibly have. Right here, game logic DLL plus offset 97E48, and then pointer offset 85C leads us to that address. It does not get any shorter than that. So if we add that, double-click that, it added down here a new pointer scan result. And I'm going to change the name here. Offline mana. We know that it's probably going to be the same in online as well, because look at what the address happened to be. The same as we found before, right? The highest address that we found before, as a matter of fact. So we can be reasonably sure that this offset will be mana no matter what. And I mean, it's more or less going to be the same every time it runs because it's the shortest path. It's not going to be looking for other memory addresses and other available offsets. This will be where it is when it starts up. So that's mana. We could do the same thing with health if we wanted to. We would need to basically do a scan for the same value, 100. And then actually let's go ahead and do it. I'm going to go ahead and get rid of all the other things that we had here for mana because we don't need those anymore. And these are other addresses that I'm not quite sure about, but I'm experimenting with, so I'm going to leave those. I'm just going to delete these. Okay, so we've got mana. Mana is on lock. Okay. Let's do health. So let's do a new scan. It's the same value, 100. We know that. So we'll do our first scan. And I can influence the amount of health I have by either getting injured or healing damage. I can't heal in this game. There's no healing mechanism. So we're going to have to go get hit. And we're going to do a decreased scan here. There should be some bears over here that would be, I'm sure, more than happy to do some damage to us. I don't want to die, so I'm just going to get hit once, twice, good enough. Okay. And the timer to begin healing is shorter, so I have time to basically get back here and run another scan. And I can maybe even do increased value compared to the last scan once I start healing here. There we go. And we have many, many paths here. I'm just going to grab one. This is our lowest address. And I'll grab the highest too. Actually, looking at the value of our mana, where our mana is stored, chances are this is going to be the lowest path for our health. Let's give it a try. Let's get rid of that first one. And let's put our checkbox here. And that should give us essentially infinite life in the game, at least the offline version. My guess is that if mana is managed server-side in the online version, so is health. But yes, in the offline version, we've certainly got it solved. They do 20 damage per hit. I can see that it's briefly flickering down to 80, but then it's going right back up to 100. So that's infinite life and infinite mana for the offline version, but for the online version, we can't because it's all handled somewhat server-side. So in order to do that, there are certain variables that we can't influence, but what we can do, perhaps, is write our own proxy and send a packet to the server that updates the status of our mana or health or something along those lines. There's no healing items in the game, as far as I know, so we can't send a packet that says we've been healed. But if we explore that, that's definitely a possibility. All right, here we are back in the town. Speed hack still on. Okay. Let's see where we're at. So yeah, different paths entirely, or different addresses entirely. So this is not in the online version where health and mana are stored. We do know, well, here's mana in the online version. Yeah, so you notice it doesn't update when we change that value. And if we resume and cast a spell, it goes right back to where it was. And if we toggle this so that it never changes, we just leave that as a static 100, and we cast spells, you'll notice that the real value will flicker once in a while, and we're already in the 80s and 70s and 60s and so on. So just not going to work for the online version because we have some server-side check or that value is being sent back down from the server. So we're going to need a proxy if we want to influence that at all. Okay. And health will likely be the same thing, but I mean, heck, let's at least find our health value. If mana is 2C BC, I almost wonder if I haven't found the health value poking around yet. We'll run a scan, sure. First scan, same as we did before, decreased value. We're going to go get hit a couple of times. Hey, bear. 1, 2, good enough. Run to safety. And it's decreased compared to the first scan. We can even have time here to do exact value 60. And then we'll do an increased value compared to the last scan once it starts ticking up. There it is. All right, we got it. And we know that mana is at 3F5, 3EFO, so 3F5, 3. This is probably our main one here. Let's go ahead and give it a try. 80. All right, that did decrease my health. Well, it didn't actually decrease my health, but it apparently decreased my health. But let's go ahead and get hit by a bear and see if it hurts us or helps us. Let's set this to 100 again. Let's make it static and try it, and we'll see if it actually works or not, but I don't expect it to. Nope. Nope. I got hit twice, and I'm down to 60. You just can't tell because it changed the update value, but health, too, seems to be stored server-side. So let's uncheck this, and you'll see in a second as soon as I begin healing. Yep. As soon as I start healing, value gets updated. But still, it's nice to know that's where the value is in the online version, because that might be useful in helping us find other variables that are useful. So we'll go ahead and pointer scan for this one too. And there we go. Notice also that in the offline version, the values for health and mana were in GameLogic DLL. And here in the online version, they're in the client. That also backs up our theory. I suppose it's not a theory anymore, but that also backs up our information that we're getting that these are handled server side instead of client side, because the client is handling those values because the client is receiving information from the server. Online health and online mana. Okay. It's nice to know where those are, though, because that helps us. You see how here's our player object, but our values for player 3F53EF0408, it's a 4-byte value. So 4 bytes for the mana, 4 bytes for the health, which means that there's probably something related to the player at 3F53EE12. Wait, no. 4 bytes hex 8 would be 9A B C, so OC. Do I have? Oh, I do have OC here. It's a 0 value, but there's something there. I'm going to go ahead and put these in order. So C, D, E, F, and then 1 O. Well, right here. That's a 0 value too. I don't know what it is, but there's something there. And then 14. Assuming that it's another. Actually, these are floats. Are floats 4 bytes? Float byte size. Usually occupying 32 bits. So yes, 4 bytes. So 1414, I should say, I don't have. So let's see what's there. Actually, let me do it the right way. So 2C, C8 would be C9, CA, CB, CD. It's another 0 value, but there's something there. Wait, where is it? Oh, did I? That's not right. Oh. Float. 4. C. C? Oh, it's C. Oh, A. Wait. 8. 9. 9A. B. Yeah, 9A, B, C, not D. My bad. Still a 0 value, though. No idea what it is. And then 1, 8. This one was CC, so CD, CE, CF, DO. There's another thing that we could do if we wanted to look for valid values. I mean, we know, for example, here that here's our health pool. We can right-click and we can browse this memory region or disassemble this memory region. And notice that takes us to this area in memory here, the address 3F53EE08. And look, here's my name. Here's my team name. This here, hex 64 is 100. We know that that's our health. If we go back up here, Here's another value. This is one way to go about it. Yeah, this at this point we're kind of stumbling around in the dark a little bit because I know where the player object is, and I'm just checking around to see what these values might represent. Not really stumbling around in the dark. It's more like educated guesses just to try and map out what we have here. There is, of course, other things that we can do. For example, if we go to Ghidra, right, as we were doing before, I guess it's time to pivot to Ghidra. We can, figure out where things should be in memory. So, for example, we're in Cheat Engine here. I know from this here, GameLogic DLL, that the address for GameLogic DLL in the instance that's running is 796400000. How do I know where these things are in memory? Well, if I go up here to the memory button, display memory map, and I go to the home button, I can rehome this. Oh crap, I forgot it already. 796400000. And that has rehomed all of this, right? So all of these. So now that I'm rehomed, if I go to, for example, well, if I go to the game world label, here's game world right here. It says here that game world should be at 796D7D7C. And I happen to have that value calculated here. And sure enough, 796D7D7C. So I know that these values are correct. I have rehomed this according to the current running process. And now I can see where these code segments should be. So if I go to another function here. Okay, well then I guess going back to our speed hack, that static variable that we saw, that is referenced in the player class. And it's used by the get sprint multiplier function. There it is, right? 3.0. That's how we found that, right? And where is that value for us to change? Well, now because we've rehomed this, we can see that it's going to be at 796B8B34. That's where that value will be. And that's where that value will be regardless of online or offline, because that's just where that value is in the code, right? So we're not making any changes. That value is in the client instance regardless of whether or not we're online or offline. It's all the same client, right? Get mana here. So it says that get mana, the value that it's putting into EAX is the value of this, so the player object plus BC. So that mana value is player object at offset BC. And look at what we have here for our mana pointer. So player object is at offset 2C from GameLogic 7 from the game world instance, and then BC. So we know that's where the value for mana is held. And even in the offline version, it's not at offset 2C for the player object. It's at offset 1C, and it's still the mana value is held at BC. And we can see that from right here within Ghidra, right here within the code. I wonder if our Pwn coins are stored locally or server side. Let's find out quick. I don't want to change gears on you too much and cause whiplash here, but let's try it. 5-3. That's the number of Pwn coins we have. 24,970 values. That's a lot of coincidental values that equal 53. We can change the number of Pwn coins we have by selling items or buying items, so let's check that out. Hello, Max. Let me turn my speed hack off here. I need guns, lots of guns. Let's see. Don't have enough for any of that. We have enough for pistol ammo. Let's buy 1 pistol ammo. There, now we have 50 Pwn coins. So exact value now is 50. Next scan. And we have only 2 values that aren't constantly changing. This is the higher address, and it's pretty close to the other values for player that we have. So let's test this out and try. Let's give ourselves 500 pwn coins. Changed in the game, so that seemed to work. If I buy another pistol ammo, will it go down to 497 or will it go down to 47? Or, yeah, 497. That seemed to work. If I sell some, I'll sell a shotgun ammo. 6 pwn coins, so this should go to 503. And it did. Let's try giving ourselves enough money to buy a gun. G17 is, well, we have given ourselves enough to buy a gun. Wow, this is a lot cheaper than I expected it to be. 313? See, that didn't work. It's not allowing me to buy it. So I think that the pwn coins updated in the client, but I think that they are also monitored server side as well. So yes, in the offline version, this would certainly work. Let's try it. All right. 1,800 pwn coins. Let's see now if we can buy the gun. Yeah, we can. Yep. So no issue then with the value itself. It's just the fact that it is recorded server side with our character instance server side. But heck, I suppose. So I guess that's one of the reasons why we don't hack the offline version in this class, because it is significantly easier. You can do pretty much anything with the offline version. Let's see. Is the gun a good buy? Look at that spread. Bearskin, pistol ammo, revolver ammo. Okay. So that proves that then. So I could keep going and adding values here to see if I can find other attributes that are associated with the player object. Or as we saw before, I can, in Ghidra, go ahead and take a look. So this didn't work. The changing pwn coins didn't work, but maybe there's something else that we can do. Also, apparently there's a chat function I wasn't aware of. I don't know of a chat here. But anyway, perform by item. What we really want, I recall when we were digging through the code on some of the first days that we saw that there was a buy value and a sell value. And that might not be something that is done server side. That might be the local instance. So if I can find those again, then perhaps we can do something with that. Oh, ivar3 equals 0. So return ivar3. That must be the value of the sell price. Well, Just Intolerable buys bearskins. Do I have a bearskin? I don't. Let's see if we can get a bearskin quick. Let's see if we can influence the sale price here and get us some money. There's a bear. Ooh, a green drop. An AK rifle, and yes, a bearskin. Okay. Well, we got ourselves an AK. Get out of here before the bears come and get me. Here, at the end of the poop chute. This, by the way, is the beginner sewer. This is just past that grate. Good place to hang out, if you ask me. All right, so we got the bear skin, and we got an AK, which is pretty awesome. We need to... All right. Well, that more or less covers then how we find these values with Ghidra and manipulate them with Cheat Engine. Scanning pointer paths, adjusting values in memory. Let's see, what else can we do? Online. Oh, we don't have a valid pointer path here for health and pwn coins anymore, but that's fine. Let's see. A couple other things that we didn't cover. So, I know that mana is being updated. I mean, there's the value being kept here. We just know that it's not updating on the server, or the server's not, or something. We don't know exactly what this relationship is yet. But let's say maybe I wanted to track it down. Maybe there's a server function or class or something in here that we could maybe manipulate from within the game to maybe send an update or something like that. Well, if you want to see what accesses an address in terms of like functions that read that value or something like that, you can go here and you can scan for what accesses this address or what writes to this address. So let's see what writes to this address. Yep, we want to attach a debugger. Yes, continue. Find out what writes to this pointer or find out what writes to the address pointed at by this pointer. How about what writes to this pointer? Real time. Oh, we do now have some things that are updating. Game API seems to be accessing that quite frequently here. It's the tick, so every tick it's checking to see projectiles in range. And from here, if we wanted to, we can actually directly adjust our assembly instructions and have it ability to do whatever we want, or just nop it out so that it doesn't do anything. Oh, there's somebody casting fireball over there. Now, in addition to seeing what accesses those address, we can see what writes to this address, and we'll do again the address pointed at by this pointer, and we'll use up some mana. See what's writing to this address. It's that game object function. It's another little part of the tool that you can use. We can, we can set hotkeys. I mean, we went and got our own trainer here so that we can set our own keys to toggle things off and on. But I mean, technically we can do that in Cheat Engine as well. So like for walk speed, I can go set hotkey and create hotkey. And how about when I press F4, set value to, and right now it's at, this is my walk speed. Yeah, this is walk speed. So we will set our walk speed to 1200 and we'll play an activate sound and apply. And then I'll create a hotkey so that when I press F5, set value to 200 back to the original, and we'll play the deactivate button. So it sounds like that. Okay, so F4 to activate, F5 to deactivate. So, I mean, technically, if you don't want to do a DLL hook, you don't have to, because with that, if I'm walking normal speed, press F4, and you heard the ding, I'm going faster, press F5, and I'm back. So you don't have to, do the DLL hook. Like I said, it's totally optional. Cheat Engine does everything that you needed to do, and there's 1,000 ways to skin a cat here. I mean, I've taught this 3 semesters. I don't think I've done anything the same way twice now. So yeah, you can do hotkeys, and that will clear that out. Or you can use Cheat Engine for that. Which actually, whatever. Show as hexadecimal, show as signed, disassemble. Okay, we can disassemble the memory region here. We can actually see what's going on. And just as before, we can change the assembly code here on the fly if we wish to. We can I guess that's about it. I mean, Cheat Engine has a lot of other functionality, but there's nothing really that we need to get into. Okay, so this has been a primer on using Cheat Engine to manipulate values, and also an explanation of what can be changed and what can't be changed depending on certain circumstances and the way the code is written. Some things are possible and some things aren't, which is why sometimes you'll get trainers that have functionality in one game but not in another. It all comes down to, what is available for changes, and how much you can cause them to bend or break, depending on the rules of the game. We saw how to find code in Ghidra, how to find values in Cheat Engine using Ghidra, how to change those, how to change them back, and at this point we have hit only one limitation, which is there are certain things we can't change client-side that maybe we might need to use other methods for, and for that we're going to need a proxy. And that means that we're going to have to stand up a VM and write a script, and that is what I will tackle next time in the next video. So it's going to take me some time to get that out, but it'll be out this week. Otherwise, take care, have yourselves a nice day, and we will see you on the next one.